Hello, everybody. Welcome back, my Chem 201 Organickers. Right now, we're going to look at a little bit of a review on hybridization. If you have not taken Chem 1, which is General Chemistry 1, Chem 121 at Harper, you have not been exposed to hybridization because in the 101 and the 110 course, that topic is not covered. That is a higher level topic. So what I'm going to do today is try to bring that down to a level that is a little bit more, a little easier for us, but gives us what we need to know for Chem 201. So all we really care about is what carbon does. So we're going to focus on the hybridization of carbon, and I'm going to give you a little bit of introduction so that you know a little bit about where this theory comes from. So let me start sharing my screen. And we are going to talk about something called valence bond theory and hybridization. So let's look at this a little bit more closely. Valence bond theory is a quantum mechanical model that shows how electron pairs are shared in a covalent bond. This model is more sophisticated than the Lewis theory model because we're actually looking at a quantum mechanical approach. It might look similar, which is actually good for us if we haven't taken Gen Chem 1 before. But this is the basic idea. If I form H2 molecule, I have one s orbital, right? H has one electron. I have another H that has another electron. I'm going to bring those two orbitals together and I'm going to form this H2 molecule. Now notice that I am now sharing those electrons, and those electrons are spin paired, just like when we put two electrons together in the same atomic orbital. When I form a molecule and I form a bond, those electrons also have to be spin paired. I could have two p orbitals that come together, right? These are s orbitals. I form this overlapping molecular orbital, which is a combination of the s and the s orbitals from hydrogen. I could also form fluorine, which is the F2 molecule, by overlapping one electron. Remember, I have 7 valence electrons. One unpaired valence electron on each fluorine is going to overlap with another unpaired valence electron on another fluorine. Here I have overlap between the p orbitals on fluorine, but I'm still forming this bond here, which has 2 electrons. Both of them are spin paired. These two types of bonds are called sigma bonds because they form from head-on orbital overlap. Oopsies. So I can also have overlap between an S and a P. So for example, if I look at HCl, right, I have hydrogen and I have chlorine. This would be in a 1s orbital. This would be in a 3p orbital, this electron. So if I just look at that unpaired electron, here I'm forming this sigma bond again, which is the overlap of the hydrogen s orbital with the chlorine 3p orbital. I'm forming this covalent bond. So valence bond theory approaches chemical bonding based on an extension of the quantum mechanical model. These are actually mathematical solutions. When these mathematically solved orbital spaces, right? Remember, the orbital is the probability that an electron is going to be found in that space. And we have really high level math, Goodwill Hunting math, that actually shows how this happens. But when orbitals on atoms interact, they make a bond. These orbitals can be very specialized hybridized atomic orbitals, which is a blend or a combination of two or more standard atomic orbitals. Covalent bonds are formed by overlap of atomic orbitals, each of which contain one electron of opposite spin, just like with the two hydrogen atoms forming H2 or the two fluorine atoms forming F2. Each of those bonded atoms maintains its own atomic orbital, but the electron pair in those overlapping orbitals is shared by both atoms. The greater the amount of overlap, the stronger the bond. When two atoms approach each other, the electrons and the nucleus of one atom is going to interact with the electrons and the nucleus of that second atom. If the energy of the system is lowered because of these interactions, the chemical bond will form. I'm always seeking a lower potential energy. Water runs downhill. A chemical bond is going to result from the overlap of two half-filled orbitals with spin-spin pairing of those two valence electrons. I can also have, although this occurs less commonly, an overlap of a completely filled orbital with an empty orbital. This is a coordinate bond or a dative bond, which is a little bit different. The geometry of the overlapping orbitals determines the shape of the molecule. As two atoms approach each other, the half-filled valence atomic orbitals on each atom would interact, and this interaction forms molecular orbitals. These molecular orbitals are defined very similarly to atomic orbitals. They're regions of high probability of finding the shared electrons in the molecule. These molecular orbitals would be more stable than the separate atomic orbitals because they would contain paired electrons which are shared by both atoms. The potential energy is lowered when these molecular orbitals contain a total of two paired electrons compared to separate one electron atomic orbitals. So let's look at carbon. Hybridization of carbon starts with the story of methane, which is CH4. If we know from our previous topics, right, this carbon is going to be tetrahedral and form 4 single bonds according to Lewis theory. So my electron geometry is going to be tetrahedral, and my molecular geometry is also tetrahedral, which means I have a bond angle of 109.5 degrees, and I have 4 equivalent orbitals. Now, if I look at the valence shell configuration of carbon, I have 4 total valence electrons and 2 are unpaired. Here's my core, here's my valence. I have 2 electrons in the S2s subshell, and I have 2 electrons in 2 of the 2p orbitals. This third orbital is empty. This is the ground state electron configuration. So how can I form 4 bonds that are basically equivalent and give me a similar bond angle of 109.5? This model here says I would form maybe 2 bonds and those bond angles would be 90 degrees, but we know that's not what happened. So what does happen? Well, let's say I produce or I add energy and I go from the ground state to the excited state. Well, this is going to promote this electron into that unoccupied p orbital. So now I have 1, 2, 3, 4 unpaired electrons, which would give me 4 bonds if it's shared with 4 additional electrons. The problem with this is that this model gives us 4 non-equivalent orbitals And we know that my tetrahedral methane actually has 4 equivalent orbitals. So something else has to be going on. And what happens is carbon actually hybridizes. I have a mixture of the 1s and the 3p, right? So this is sp3, 1s and 3p orbitals combined. And what I get is S4 sp3 equivalent orbitals. So now I can have bonds to each one of those unpaired electrons in each of those 4 degenerate or equivalent sp3 orbitals. So sp3 hybridization, the mixing of an individual 2s with the 3 orbitals in the 2p subshell, give me 4 equivalent sp3 hybridized orbitals. And that's how I can explain how methane is formed. If I look at this, right, here I have unhybridized, where I have 2 electrons in my S and then 2 electrons in the P. This is going to mix and change, so I have, and hybridize, so I get those 4 equal energy sp3 orbitals. That's going to look like this. And notice now I have this tetrahedral geometry. Now, when I form CH4, each one of these hydrogens is going to share its 1s electron with each unpaired electron in an sp3 hybridized orbital. Now, according to valence bond theory, bonding takes place between atoms when their atomic or hybrid orbitals interact. This causes overlap. But as we're going to see as we continue, there are 2 different types of interactions. We can be head-to-head, which means the 2 overlapping orbitals are aligned along the axis between the atoms. Or I could have sideways overlap, where my 2 interacting overlapping orbitals are parallel to each other and perpendicular to the interatomic axis. I'm going to show you what that means in a second. All right, so any atom that has 4 electron groups around it is going to adopt my tetrahedral geometry, and I'm going to have 109.5 degree angles between hybrid orbitals. Atoms are going to use these hybrid orbitals for all bonds and lone pairs. This is what we just talked about. This is methane. I have my 4 equal energy sp3 hybrid orbitals with this bond angle of 109.5. That's going to overlap with each one of these 4 hydrogen orbitals, and what I get is my methane molecule. I could also do this with, remember, ammonia, which is electron geometry is, where did that come from? Electron geometry is tetrahedral, but my molecular geometry for ammonia is trigonal pyramidal, right? And notice I have a lone pair, right, in an sp3 hybridized orbital. So this is NH3, right? This lone pair is in an sp3 orbital. This is an sp3, this is an sp3, and this is an sp3. And then it's overlapping with the hydrogen S's, right? In water, I have the same thing. But now both of those lone pairs, right? I have a lone pair here and a lone pair there. They're both in sp3 orbitals. So I still have the same sort of premise that I had with Lewis structures, but now I've expanded it. If you look at these hybridizations, right, you can clearly see that for NH3, one of the lone pairs is going to be in the sp3 orbital, and here I have two lone pairs, two bonds that form. Here I have one lone pair, three bonds that form, which obeys the bonding rules that we talked about when we discussed Lewis structure. So this hybridization scheme can account for the bonding that's seen in any tetrahedral molecule, any electron geometry that has 4 charge clouds, even if the molecular geometry is different because it has unpaired lone pairs. Those unpaired lone pairs, those non-bonded lone pairs, are going to be residing in hybridized orbitals in these cases. Well, what if I have trigonal planar, right? Remember, carbon can also form trigonal planar geometry where I have 2 single bonds and 1 double bond. Well, let's look at this. If I have a hybridized and unhybridized carbon, let's say I'm going to take one of the s orbitals and 2 of the p orbitals, and I'm going to hybridize that way. So if I combine this, I'm going to get 3 sp2 because I combined 1 s and then 2 p's. And then I have this unhybridized p orbital that still remains. I can do this for oxygen as well, which means that I will have 2 lone pairs in the sp2. Here I have the potential electron for bonding, and I also have oopsies. I also have 1 electron in my unhybridized p orbital as well. This gives me this trigonal planar geometry. What happens is these sp3 orbitals form that trigonal planar geometry. I have my unhybridized p that is 90 degrees from that. So if I take my 2 s's and I add it to 2 of the p's, what I'm going to get is an sp2 orbital that forms a trigonal planar geometry. Here, I still have the unhybridized p. Now, let's look at this again. I combine the 2p and then that s orbital. I'm only combining 3 orbitals. This gives me sp2. I still have the unhybridized p orbital available. So these hybrid orbitals will overlap on the axis with orbitals from the other atoms. My unhybridized p orbital is going to do that sideways overlap, that side-by-side overlap. And that's how I get a double bond. So here's my sigma bond, which is my head-to-head overlap. And here's my sigma bond, which is my p unhybridized to p unhybridized overlap. This is going to be the double or the double and the triple bond. I always have a sigma bond, and then if I have a double bond, I'll have a sigma and a pi. And if I have a triple bond, I have 1 sigma and 2 pi sidewise overlaps of those unhybridized p orbitals. So my sigma bond results when the interacting atomic orbitals point along the axis connecting the 2 bonding nuclei. And my pi bond results when the bonding atomic orbitals are parallel to each other and perpendicular to the axis that connects the 2 bonding nuclei. That is a side-to-side overlap. these side-to-side parallel orbitals are not as strong. So one thing we know is that sigma bonds are stronger than pi bonds. Now in carbon, this is going to be important. This is going to be how I look at this trigonal planar geometry. I have one sigma bond, and then I have a pi bond, right? So between the carbon, I have the sigma bond, and then I have a pi bond. This is going to be the sideways overlap. This is going to be the head-to-head. So what I notice here is that I have a double bond, right, which is how carbon forms a trigonal planar geometry. This is always going to be from an sp2 hybridized carbon. As we said before, oxygen can do that as well, right? So in this model, one of these is going to be a sigma bond, the other one is going to be a pi bond, and my two lone pair are going to be in other types of orbitals on oxygen. So my double bonds always have one sigma bond, which is head-to-head overlap, and one pi bond, which is going to be a side-to-side overlap between p orbitals. Now the overlap between these hybrid orbitals on one atom with a hybrid or non-hybridized orbital on another atom is going to be that sigma bond. And then the orbitals between the unhybridized p. These sigmas always form with those hybrid orbitals on carbon or oxygen. And then my unhybridized p orbitals are always going to result in, when they overlap, they give me that pi bond. Now pi bonds are interesting because they have restricted rotation. Because they're above and below the internuclear axis, right? If I have my two nuclei and I have this sort of bond that's sort of above and below this, right? I can't actually rotate. There's no rotation here. Otherwise, I broke the bond. If this sigma to sigma, this one I can twirl around and rotate, it's okay, as long as I don't have this pi bond. If I have the pi bond, that pi bond can't rotate without breaking. So that gives me some interesting possibilities when I have a double bond. Unhindered rotation. We're going to see that if I have, this is sp3, this is sp3 tetrahedral, right? They're both tetrahedral. 4 sigma bonds. This can just twirl around. This bond can just twirl around freely. And that chlorine can be anywhere in the space around there. And it's not gonna, it's just gonna freely rotate. Here, because of this pi bond, I have restricted rotation, which means that these two molecules with the chlorine on the same side or the chlorine on opposite sides, these are actually different molecules. I cannot simply rotate those in order to make them from one into each other. In order to go from the same side to the opposite sides, I actually have to break that bond, which is something that is going to take energy and require a chemical change. And it's just not a single rotation. There's one more type of orbital, right? If I have, if I have carbon with 2 double bonds, or if I have carbon with a triple bond and a single bond, right? This is my linear geometry. This always results from sp2. I take one s and one p. I have 2 unhybridized p orbitals. So this gives me those 4 valence electrons. These are going to be forming my linear sigma bonds. These are going to form my pi bonds, which can be either the double, or I could have 2 pi's and I could have a triple bond. So what this looks like is this. Here is that linear sp to sp. Then I have a p orbital going up and down, a p orbital going in and out. Remember, this is a three-dimensional geometry. These two sp2 orbitals are going to be oriented 180 degrees. This gives me my linear geometry, is always an sp hybridized atom. This is acetylene. If I take hydrogen and then I go with a triple bond to another hydrogen, what I'm going to get is a sigma bond, and I'm going to get 2 pi bonds. This is going to be between the head-to-head overlap of the sp2 orbitals on each carbon. This is going to be the p to p in the x direction and the p to p in the z direction in order to give those 2 pi bonds. So hopefully you can see I have a pi bond that's sort of up and down, and then I have a pi bond that's sort of in and out, and then I have my linear sigma bond across the top, or across throughout those orbitals. So this is also what it looks like. Maybe you can see this a little bit differently. These P's are at 90-degree angle. One is up and down, one is in and out. And then I have this linear geometry of those sigma bonds according to the valence bond model. So again, anytime I have sigma, it's the hybridized orbitals. If I have pi, it's going to be the unhybridized p to p sideways overlap. So this is basically what you need to know right here. If I have 2 charge clouds, I'm going to be linear. That's usually a result of sp2. If I have 3 charge clouds, that's going to be trigonal planar. That's going to result from hybridization into sp2 orbitals. And then if I have 4 charge clouds, that's tetrahedral, and that gives me those sp3 hybridized orbitals. So this gives me the carbon that looks like this. It gives me the carbon that looks like that, or it gives me the tetrahedral carbon where all 4 bonds are single bonds. This right here is what you need to know for this course. If you can remember that double bonded, 2 double bonds, or a triple and a single is from sp hybridization, and that gives me a linear carbon geometry. If I have 3 charged clouds where I have 2 singles and a double bond on my carbon, that gives me, that results from sp2 hybridization. And then my tetrahedral geometry, my 4 single bonds with those 109.5 degree bond angles, results from sp3 hybridization of carbon. You will be good to go. So that is all I have, and hopefully that brings some clarity to those of you who have not taken Chem 1 and have no idea what hybridized orbitals are. Again, don't be too scared off by this concept. We really only need to know a limited amount. I went into a little bit more depth here because I wanted to give you an idea of the theory behind it. But basically, you need to know this slide. And then if you just know this correlation between the number of charged clouds, the geometry of those charged clouds, and then the type of hybridization, and really only for carbon, you are good to go with the rest of the class. See you soon.